So welcome back. Let us proceed with our second presenter. As usual, I will share some of his background before he presents his paper. Our next speaker, we are very fortunate to have Dr. Chanakya Arya. He is a chartered engineer and a member of UK Institution of Civil Engineers. He has a Bachelor of Civil Engineering from Birmingham University and a PhD in Civil Engineering from Imperial College of Science, Technology and Medicine. He started his career with Tamak Construction Limited as a site engineer. Later, he joined G. Mounsell and Partners and worked both on site and a design office. After 2 years, he took up appointment as a lecturer of civil engineering at London South Bank University, and he has been there for more about 10 years. Now he is lecturing at University College London, and he has been research for the past 20 years, and his focus area will be on reinforcement corrosion of steel in concrete structures and developing demonstrable cost-effective methods of assessing corrosion and preventing and repairing and managing stock of concrete structures vulnerable to corrosion damage. So ladies and gentlemen, with that short introduction, without further ado, I would like to call upon Dr. Arya to make his kind presentation. It's over to you, Doctor.
Okay, thank you, Chairman. I hope everybody can hear me. Good morning, everybody. Before starting, I'd just like to thank Dr. Zuhairi, who I've just seen, and the rest of the organising committee for inviting me to this event and for allowing me this opportunity to present this talk, which, as you can see, is entitled "An Aid to Understanding the Concept of Sustainable Design for Engineers." The aid that I'm referring to is a suite of exercises that we've developed that are designed to help civil and structural engineers develop a deeper understanding of the concept of sustainability and sustainable development, thereby allowing them to deliver sustainable designs. The exercises themselves are actually based on a case study which was carried out as part of a research project to develop a sustainability appraisal tool for civil engineering structures called SAS. So, in fact, there are two main items to the talk that I'm going to be presenting today. So I'm going to be describing this tool called SAS, and then I'm going to be describing the exercises that have subsequently been developed. This overhead just shows the outline of the talk. I'm going to begin by addressing the question, why should built environment professionals engage with this agenda? Seems like an obvious starting point. I'll then talk briefly about this appraisal tool SAS, which I've just mentioned, before going on to describe the case study that was carried out and the suite of exercises that have been compiled. I'll present some results, summarize, and finally conclude. I seem to have lost my way. I wonder if somebody can help me. There we are. That's fine. So, relevance to the construction industry. I think it's true to say that the construction industry receives extensive attention from all those who wish to promote sustainable development. The reason for this is fairly obvious when we start looking at some of the statistics for the construction industry. Now, if we take the UK construction industry as an example, it constitutes around 10% of GDP. It employed around about 3 million people back in 2008. I think the numbers have probably dropped slightly because of the recession that Europe is going through. And in 2000, it was estimated that the construction sector was estimated to consume around 6 tons of materials per person per year. Moreover, the industry generates large amounts of waste and emissions, and construction and maintenance activities can have a significant effect on local communities. So all of these aspects, as I'm sure you know, are relevant to sustainable development. And given the scale of the impacts involved, it's little wonder that the construction industry receives extensive attention from all those who wish to promote sustainable development. Over the years, many ways have been proposed to coerce the construction industry and indeed other sectors of industry to comply with this agenda, but the response has been rather flaky. Our assessment of the current position is, as sort of summarised here, that it's engineers are certainly all very aware of the impact that they have, but it's very difficult to comply with this particular agenda. There are such a large range of factors that they need to consider that it's not clear which direction that they should go in or which factors should be adopted. The fact that there's no clear methodology also militates against sustainable development. So in the impasse, engineers continue to produce designs which are focused on technical and economic issues. They pay lip service to the fact that they're being sustainable. If you look at any website produced by consultants, they'll have a lot of emphasis on the fact that they're engaging with this sustainable development agenda. But essentially, what you find is that they're doing what they always used to do, but they bring out the bits which are relevant to this agenda, and then they say, well, we're being sustainable. But to be fair to them, it's not because they don't want to, but a lot of the time it's just there is really no clear methodology which is available to them. So our proposed solution to this has been to, overall, that actually more education is needed. So engineers do have an understanding of some of the concepts, but really they need to develop a deeper understanding in order to engage with this particular concept. And this these suite of exercises that we've developed are an attempt to do just that. They're unlike the previous speaker. These exercises are relevant to structural design, so they're aimed at that community, and we're hoping that these exercises will enable, as I say, engineers to develop a better understanding of the concepts involved, and thereby help them to deliver sustainable designs. I also said at the outside that the exercises are based on a new sustainability appraisal tool called SAS, and so it seems appropriate. I'm sure you're not familiar with it, so I'll just spend a few moments describing what this tool is. Well, this overhead here just shows you the general structure of this particular tool. The boxes in green indicate the indicators that are used to assess sustainability in this tool. They're grouped under the three key themes that we normally associate with sustainable development. So you've got environmental protection, society, and economy. When we were developing this tool, what we wanted to do was to make the assessment of each of these factors as numerical as possible. There were a number of reasons for trying to do that. One was that we wanted to was to improve the reproducibility of the assessment and reduce the subjectivity. If you look at some of the other tools which are available, what they tend to do is they tend to use woolly words, significant, this, that, and the other, which tend to put engineers off. We're used to numbers, we're used to precision, and so that was the reason why we wanted to make the assessment as numerical as possible. Now, when you look at some of the procedures, you may disagree with it, but we've said we've set out our stall, and this is the way it's done. And if there are improvements that you feel are necessary, well, you're at liberty to do just that. Now, it'll if I look a little bit closely at a couple of these indicators, you'll see you get a bit more feel for how this tool works. So, as far as the environmental indicators, as you've seen, there's climate change, resource use, waste, and so on. As far as climate change is concerned, the way that we've quantified that is by assuming that climate change is equivalent to CO2 emissions. And what's recommended in the model is that the CO2 emissions associated with the materials required for construction and materials required for repair of the structure are taken into account. There are various other transport-related properties, transport-related issues, which are also considered. So, transport of materials from the factory gate to the building site, the plant used during construction, transport for disposal of construction and demolition waste, transport for employees from home to building site. So these are all sort of transport-related issues. The third one, which appears right at the bottom, is congestion. As I'm sure you all know, that when there's construction work going on, and particularly with repair work, there's always periods of congestion, and as a result, what will happen is that the traffic will be slowed down, and there will be extra emissions over and above what would normally be the case if the traffic, if that piece of construction work wasn't going ahead. And so those are the three elements that we've suggested should be considered in calculating the CO2 emissions. Under resources, well, there are a number of items that are included here. So we've got energy and materials, land and water. Now, as far as energy is concerned, it's the energy which is associated again with manufacturing the materials necessary for the construction and for the repair of the structure, for the various transport issues that I've just been going through, and also for congestion. Again, traffic is being impeded, and as a result, there will be extra fuel which is being used as a result of the driver slowing down, and particularly when it comes to stop-start driving. As far as materials are concerned, well, it's going to be based on the amount of materials, but also the source of the materials. So materials which are derived from virgin sources, we've suggested, should have the highest impact. Where you've got materials which are being sourced from recycled sources, they can have a lower impact. And where you're using materials which don't require any processing, so for instance, if you're using, say, an existing steel beam and it's being taken from one location to another, then it won't attract any penalties. In some structures, we may be able to utilize existing foundations. So that will help to reduce the impact of construction work. And we've done a similar kind of thing for land and for water. We tried to identify what are the factors and come up with a way of scoring each of these items. Under society, if you remember that list that I showed you, there were 4 items: dust, noise, vibration, and aesthetics. And as far as dust, noise, and vibration are concerned, the impact here is generally assessed in a very similar fashion, and those are the the items that we've suggested should be taken into account. So the net increase in the level of nuisance, so be it dust, noise, and vibration. So look at what the ambient dust levels are and what the maximum dust levels are likely to be. So that will give us the net increase. The duration of the nuisance, so during construction and during subsequent maintenance. The presence of any sensitive premises nearby. So you may be building somewhere which is close to a hospital or close to commercial development, or it could be an educational establishment. So if you're making noise, you're going to be causing disruption. Now, just before coming, I went to visit a site in Victoria, and so this Victoria in London, and there's a big development going on just there, and it's very close to 2 theatres, and there are very, very stringent requirements that are in the specifications to limit the vibration. And so if the vibration go above a certain level, it's going to cause a nuisance to people sitting in the theatre, and so the contractors, if they exceed those, will get penalised. So effectively what the contractor has done is that he suspended work on the days when there are matinee performances and on Saturdays to avoid having to pay these penalties. So these are real costs. The last item on there is public consultation. So you can mitigate the effect of nuisance by having somebody who's making the residents aware of the nuisance, and that they've got somebody to come to if they find that the nuisance becomes intolerable. Contractors' past performance. So these are all based on some guidance that we found. Economics. Under economics, we've got a number of indicators there, and one of them being traffic delay costs. Now, I mentioned to you just a moment ago that that when construction work is going ahead, then there will be some disruption to traffic. It will not only result in increased CO2 emissions and increases in energy consumption, but it will also delay traffic. And if there's commercial traffic, it will increase journey times, and which will mean that there'll be more wear and tear on the lorries, and because the journey times are being increased, so the cost of the goods that are being transported will increase. So there are procedures that have been developed in the UK by the Highways Agency, which enable these costs to be determined, and these are some of the factors that that you can use to actually put a number to the cost of these delays that will arise. So that's just giving you an overview of what this little tool that we've developed, SAS, is about. As I say, we've been trying to make this assessment as numerical as possible. When we were developing this, what we did to just test the methodology was to carry out a case study, and the case study has formed the basis of these exercises, which I'm going to describe in a moment. But essentially, what this case study was about was that we took this cross section of a dual two-lane motorway, and we imagined that we needed an overbridge at this particular location. And we made some assumptions regarding the motorway and also the bridge that was required at this location. So as far as the bridge was concerned, it was supposed to carry a two-way access road. So the carriageway width would be 7.33 meters, and there was an additional requirement that there should be 2.5 meter wide footpaths on both sides. We assumed that the motorway had a traffic flow rate of 80,000 vehicles in both directions. So that's an annual traffic flow rate, of which 20% are heavy goods vehicles. And as far as the access road is concerned, so that's the road on the bridge. We assumed that that it carries 6,000 vehicles, of which 10% are heavy goods vehicles. The bridge is located in an area of outstanding natural beauty, and it's going to be in a fairly prominent position, and so we wanted an aesthetically pleasing solution. And we further assumed that the bridge site is close to a hospital. So we came up with three alternative schemes for the bridge at this location, which are just shown on this overhead. So if I just turn to my notes for a second. So as far as Bridge 1 is concerned, it's a 64 meter long, 25 millimeter thick continuous reinforced concrete deck, which acts compositely with 4 steel universal beams. And the substructure comprises integrated bank seat abutments, and there are 3 intermediate wall piers. Bridge 2 is 2-span, as you can see. It's 32 meters long. And this one's simply supported. So whereas Bridge 1 is a continuous deck, Bridge 2 we've assumed to be simply supported. It's got closed-end cantilever abutments with wing walls and intermediate wall pier. Bridge 3 is as you can see, 3-span. It's made of in situ voided slab. There's a bank seat at one end, and there's a cantilever abutment with wing walls at the other end. And there are intermediate supports which are made of columns and crossbeams. So those are the 3 alternative schemes that we came up with for this particular location. And the question was, which of those 3 options is the most sustainable? What we did in the analysis was to consider 2 phases of bridge provision, so construction and in-service. And as far as the construction phase was concerned, we assumed that the motorway is closed, so there's not going to be any disruption to the traffic on the motorway during construction. But obviously, when there's maintenance work required, then that is going to give rise to disruption. Now, getting on to the exercises, in total there are 10 exercises that we've devised. Exercises 1 and 2 are similar in that they are concerned with calculating the CO2 emissions related to material usage. So exercise 1 looks at the material usage associated with the construction of the bridges, and exercise 2 looks at the CO2 emissions associated with the repair materials. So there's an example which is given, which shows you how to calculate the CO2 emissions. So it's relatively easy. You've got mass of materials times the emissions factor, the production emission factor to give you your CO2, and energy can be calculated by multiplying the mass of materials by the production energy factor. Now these kind of factors have been produced by a number of organisations in the UK, the University of Bath being one organisation, but there's DEFRA, there's another organisation whose name escapes me, but anyway, there is data available. So if you know the mass of material, then you can go ahead and calculate the CO2 emissions and associated energy. So as far as Bridge 1 was concerned, having given an example, then we itemize the amounts of aggregates required to construct that bridge. We assume that the deck is reinforced with stainless steel, so the amount of stainless steel required, the steel beams, steel reinforcement, waterproofing, and so on. And so the person using these exercises can go ahead and calculate those quantities. Exercise 2, as I say, is similar, but deals with the repair materials. Exercise 3 is calculating the CO2 emissions due to congestion. So again, I've mentioned this a few times, that during maintenance work there is disruption to traffic, and we've been able to come up with a procedure which enables the amount of CO2, the extra CO2 which is produced, to be calculated. So it depends on things like the duration of the maintenance work, the length of the road which is going to be affected, the traffic flow rates, the timing of the work. So if you can carry out the work, say, during off-peak hours, then the impact is going to be less. If you carry out the work during peak hours, well, the traffic flow rates are going to be higher, and so the impacts are going to be higher. So there's an example calculation which is provided, and the one that you're looking at relates to inspection. And you can see that we've got 92 days, and the way the 92 days are derived is that we're assuming that inspections of the bridge is carried out every 5 years. The bridge has a life of 120 years, and so in order to reach that life of 120 years, there will be 23 times the bridge will need to be inspected, and where we further assume that it's a 4-span bridge, and so we're going to need 4 days to inspect that structure. So the 23 times 4 gives us the 92 days. In order to carry out the inspection, we're going to have some lane closures, and we've assumed it's going to be 0.2 kilometers. The percentage of heavy goods vehicles, the traffic flow rate on the bridge is 80,000, and of which 20% are heavy goods vehicles, and so that's where the 16,000 comes into it. We're assuming that we'll be able to carry out these inspections during off-peak hours, probably at weekends, and so so there's an off-peak coefficient of 0.25 which has been introduced, and then there's a CO2 per HGV which we've been able to determine from published data. We also found a piece of research which suggested that there was probably going to be a 30% increase in CO2 emissions as a result of congestion, and so by that means we can calculate the extra CO2 emissions and the extra energy that will arise. So those are sort of all, everything is kind of numerical. Alongside these exercises, we've we've asked questions as well. So you're getting this data, and getting the person producing this data to see, well, what is it? What is this data suggesting to you? So decide whether construction or maintenance has the most effect on the environment over the lifetime. So this data is being collected during those first three exercises, and have a look at that and see what can be what you need to target if you want to reduce CO2 and energy use. So it's meant to be reactive. So these tools are meant to be. So you're looking at it, you're analysing, and then deciding, well, what can we do to change our design in order to reduce the impact? So, as I say, there are some are relatively closed-ended questions, some are slightly more open-ended. We've got exercises 4 and 5, which deal with cost. So there's the cost of maintenance work. So that will include the engineering costs. It will include the cost of access. It will include the cost of overheads and traffic management. So those are the 4 items that are considered to make up the cost of maintenance work. And so there's an example calculation which enables you to estimate what the cost of carrying out these 23 inspections that I was saying to you over the life of the structure would be. So the cost of a single inspection is £12,100. So if you multiply that by 23, you end up with a lifetime cost of £278,300. And what we normally do is we discount those back to the base year, which is normally the year of construction. Again, there's guidance provided to do that, and the same exercise can be repeated for other items of maintenance work. And in our case, we've assumed that we need to carry out concrete repairs, we need to carry out painting of the steel beams, and we need to carry out drainage cleaning. The other cost are the cost of these traffic delays, and again, there are well established procedures for calculating the traffic delay costs. So let me just carry on. So this is there's an example calculation which is provided, which enable you to calculate what the traffic delay costs are for inspection, and then you can go ahead and work out the cost for the other things. Exercise 6 deals with aesthetics. We've been able to draw on some guidance which has been produced by the Highways Agency, by the Australian Roads and Transport Authority, and from these guidelines you can assess the aesthetic qualities of bridges. Exercise 7 deals with dust, noise and vibration, and I mentioned some of these factors to you, and as we've made some assumptions about what the ambient dust level is, what the maximum expected is, where the bridge is, when the work is going to be carried out, if there's going to be a liaison officer, and the duration of the nuisance. And that enables a sustainability score for dust of 738,000 units. So having gone through those exercises, at this point, you will end up with a table of results which look a bit like this. So you've got quantities of the CO2 emitted, you've got quantities of the energy consumed, the materials consumed, dust, noise, vibration, aesthetics, construction costs, maintenance costs, traffic delay costs. Now the thing is that if you want to arrive at a sustainability score, you need to be able to add up those units. And they're all measured in different quantities. And so what we did was, what we've suggested is that you normalize them. And this involves dividing each of the scores by the sum of the scores for the other 3 bridges. So there's a little calculation there which is shown, and if you take it away from 1, you end up with a normalized score for bridge 1. You'll see the details of this in the paper that I've handed out to you. So we have another exercise which looks at so we've done the normalizing. Now before we work out the sustainability score, what we need to do is to take account of the fact that we've got 3 environmental indicators, and we've got 4 societal indicators, and 3 economic indicators. And so if we were to just sum these up as they stand, you would have a bias towards the societal indicators. And so what you need to do is to weight the scores. So assuming that the environment has an equal weighting, and it's a third, so if you divide a third by 3, you end up with a weighting of 0.11. And with society, again, if you divide a third by 4, you end up with the 0.083 figure. And by multiplying the weighted score by the normalized score, you end up with the final score, and which can then be summed in order to come up with a sustainability score. So this is a results table that we found with this going through this particular exercise for these 3 bridges. So the score, the highest score, represents the most sustainable solution. So looking at it, you would think that bridge 2 is the most sustainable. You can go further and look at the impacts under the environmental category, under the societal category, under the economics category, and see whether all those figures there are telling you the same story. And in fact, if you do that, you'll find that bridge 2 seems to score the highest. Now the only one which sort of sticks out here is the impact of aesthetics. And what you find there is that bridge 2 scores lower than bridge 1. If you remember, bridge 1 was the one with the 4 spans, bridge 2 was the 2-span structure, and bridge 3 was the 3-span structure. And bridge 2, from the guidance that that is available, we've been able to classify as being the most aesthetically most pleasing. And if you look at the costs, so if you look at the cost of construction, bridge 2, because it's only 2-span, and the way that we've costed it, it's 50% cheap. It's 50% cheaper than bridge 1. But if you include the cost of maintenance, you find that bridge 2 is only 10% cheaper. Now, these numbers are based on certain traffic flow rate, and if you were to look at do some kind of a sensitivity analysis, you may find that the figures aren't that far apart, and in which case bridge 1 might be a better option, because given its sensitive location, that's going to be a more pleasing structure for this particular location. So, and the final exercise is looking at that if the economy is constrained, then what you might want to do is to change the weighting, so that you give the weighting, you give the economy a higher weighting than, say, the environment and the society, and see what the effect is on the sustainability score. So, so just to summarize and conclude, so many engineers continue to develop schemes that consider technical and economic factors and ostensibly ignore environmental and social factors, because A, it's not clear which factors should be considered, and B, how the impacts associated with each of these factors should be measured and accounted for in design. And the talk has highlighted some of the more important factors that are relevant to civil engineering projects, the methods of assessing the impacts of each factor have been developed, and the exercises attempt to show the steps involved in carrying out a sustainability appraisal and the diverse and far-reaching effects that design decisions can have on lifetime sustainability. And they also attempt to highlight some of the interrelationships between the various factors considered. So in the exercises, what we've done is we've said that if you want to reduce the environmental impact, how could you do it? And then what will be the implications of that change, proposed change, on the economics of the design and on the societal impacts of the design. So these things are, it's complex. What can I say? It's not an easy thing to do. And all we're just trying to do is to bring these aspects to the fore. Now this is, I've gone through this in a very kind of laborious way, but I think the essential thing about this is that because it's new, it looks long and tedious, but with a bit of experience, I think it'll become second nature. And in fact, what we've done here is that we've carried out an appraisal of the three designs. But really, what you need to do is to be thinking about these factors before you actually put pen to paper. That what are we trying to achieve in order to come up with a sustainable design? Because once you've designed it, it's too late. So, so that's the last point. The SAS, like other appraisal tools, can be used to appraise the sustainability of completed designs, but can also act as a guide to producing sustainable designs. Now finally, what our analysis has actually showed us is that if you want to produce a sustainable design, one of the ways is to increase the durability of construction. So if you increase the durability of construction, then you will require less maintenance, and if you require less maintenance, there's going to be less noise and dust and disruption. There's going to be less CO2 produced as a result of congestion. There's going to be less energy use. So durability seems to be the way of improving sustainability. So that seems to be something that came through from our analysis. But the other thing to bear in mind is that generally, if you increase durability, you will probably increase the cost of construction, which may not always be affordable. So that's also something that you need to bear in mind. Okay, I've certainly gone over my allocated time. Thank you for that.
Yeah. Thank you very much, Dr. Arya. Very interesting. All the while we have been talking and listening to about green building assessment tool. I think this is something I don't know. I consider something is over and above that. I think this is more on sustainable. Huh? Mm-hmm. Okay. Since we have a problem of time factor and 45 minutes, but anyway, I will just allow one question, if any, from the members on the floor. Anyone? Anybody would like to ask questions? Yes, please, miss.
Okay, hi and very good morning. I'm Marati from UITM. I'm a PhD student doing my research in green initiative development. Basically, I think that I could understand the whole picture of this study. We're talking about the carbon emission, the potential of carbon emission itself to the construction, to the economic benefit as well. Talking about the qualitative and the quantitative value of this study. The rationale, actually, the rationale of this study towards the carbon emission reduction in Malaysia. Let's be a realist. You are talking about the transportation of the materials to the site, that transport during the non-peak hour. So what is the construction period in construction activity and construction period is 8 to 5. So they need to deliver all the materials during 8 a.m. to 5 p.m. whereby let's say during 8 p.m. until to the 6 a.m. is the best non-peak hour to deliver the materials. So how actually to position the idea of giving the extra time to the contractors to deliver the materials during the non-peak hours in Malaysia. So actually this idea to position to the authority giving that time to the contractor. For you, how actually to position that idea to the authority maybe in Malaysia to give more extra times for material delivery? Thank you.
Okay.
Okay, Doctor.
I think it would be a hard sell, and if you just remember the conclusion that I was coming back to right at the end, was that a lot of the time we seem to be looking at the wrong thing. A couple of years ago, I was in China, and they're doing a lot of research in trying to come up with alternatives to cement, because cement production requires a lot of energy, which gives off lots of CO2 emissions, and in order to produce cement, what we're doing is we're burning calcium carbonate, which also produces lots of CO2, and so as a result, they are doing a lot of research trying to move away from calcium carbonate cements. And I mean, they're not alone in that. The UK is doing some of that stuff, and it's very interesting research. But what our analysis here was showing was that if you look at the bigger picture, the CO2 emissions from the cars far exceeds the CO2, the embodied CO2 from cement production. So globally, it's maybe represents about 5% of total CO2 emissions, and that's why people have been looking at the impact. But actually, that isn't where the problem is. The problem really lies in the lack of durability of our structures, and that is something within our control. We can calculate the CO2 emissions to do with delivery, and they pale into insignificance. But when you talk to sustainability experts, they will start saying, "Have you considered this? Have you considered this? Have you considered this?" But we have considered it, and we've got the numbers here to prove that it's just tiny, and we need to move on from these kind of considerations. So I'm not sure whether that helps. A little bit. Okay.
Okay, maybe you can chit chat with Doctor later. Okay, Doctor, thank you very much.